Should I send out a reminder?
Yeah, maybe. Ended. It may not be thinking. Oh, it's already live on YouTube.
Yeah.
I see. Okay. Then maybe we should, maybe you can send out a reminder, but we can start. Yichun should be here. What? Is Yichun in the office?
He's doing the TFT final.
Oh, she's doing the final.
Yeah.
That's why. I see. There are some take-home exams today. Oh, well. All right. Okay. So, well, it's very excited to have Tim here. There aren't many people in the room, but people tune in from Zoom, and this is live recorded on YouTube. So it becomes available for people to watch afterwards. I just found out there are some exams going on right now because it's a final week. So maybe not everybody is going to be tuning in real time, but nevertheless, I think there will be a lot of interest. So without without more, Tim is a scientist at Sandia National Lab. He's part of this quantum performance laboratory, where they have been making really leading contributions to dealing with qubits and especially understanding what can you do with gates. Without more, please, Tim.
Thank you. So thanks for the invite. I'm going to be telling you about learning the capabilities of quantum computers today. There we go. So this talk is going to be about kind of 3 different sections and about 3 different papers on arXiv and something that's also in preparation. So I'm not going to be going into huge detail about any of these results naturally, as we don't have all day. Also, if anyone has questions while we're going along, feel free to interrupt me if I don't get through everything. That's totally fine by me. So the first part of the talk, I'm going to be telling you about probing the capabilities of quantum computers using mirror circuits. So this is work that we published in Nature Physics in January. What I'll be telling you about in this section is what do we mean by a quantum computer's capability? And then I'm going to tell you about mirror circuits, which are an efficient method for probing capabilities that we developed. And then I'm going to tell you about some experimental results where we use these methods. Then in the second part, I'm going to tell you about using mirror circuits to estimate algorithm execution fidelity. So with what fidelity can you execute some algorithm on a given device? So this work is in 2 separate papers. So part of this, I'm going to be telling you about how you can use randomized mirror circuits to measure the infidelity of individual circuit layers, so the average infidelity over a set of layers. So this is a kind of randomized benchmarking. That's in the first of these 2 arXiv papers. And then I'm going to be telling you about how you can use a specially designed mirror circuit ensemble to measure the fidelity of a complete circuit. So you can then say how well you can run this entire circuit. And then the third part of the talk, which is going to be pretty brief, I'm going to tell you a bit about learning a quantum computer's capability using neural networks. So the idea here is that we're training neural networks on labeled data where we have circuits associated with their fidelities that we've measured, and then we want to predict the fidelity of untested circuits. And I know that some people here are interested in applying machine learning to these kinds of problems, so I thought I'd share our recent work on this. Okay, so naturally I'm going to start with the first topic, probing the capabilities of quantum computers using mirror circuits. So all of this work is motivated by a really high level question, which is people really need to know what a given quantum computer is capable of doing. So for example, someone might be trying to sell you their quantum computer, or you might be spending your valuable grant money buying time on a machine. In the future, hopefully there will be useful quantum computers that can actually run useful algorithms, and you want to know what problems they can and can't solve. And so from the perspective of someone who's going to use a quantum computer, you need to be able to answer the question, what applications or algorithms can this device run? there's lots of different things you might want to be doing. You might want to run random circuit sampling and publish a flashy result in Nature. You might want to be doing quantum error correction to try and build logical qubits. You might be trying to run some NISQ algorithm. There's all sorts of different things you might be wanting to do, and you need methods for actually measuring, can this quantum computer do this or not? So in this talk, I'm going to be talking a lot about quantum circuits. So most people know what I mean, but just to make sure we're all absolutely clear about this, as it's kind of critical to everything happening here. So a quantum circuit, it has a circuit width, which is the number of qubits that it acts on. It has a depth, which is the number of logic layers in the circuit. And a circuit just consists of a sequence of logic layers. And importantly, a quantum circuit is not just the same thing as a unitary. So it implements some unitary. We're only going to consider unitary gates in this work. But what it actually is a sequence of instructions. So you have to apply this sequence of instructions. That's what the circuit means. So for example, you could have a really complicated circuit that implements an identity unitary. If you run that circuit, it still means running all of those layers, because that's often important when you're doing things like benchmarking, where you design circuits that actually implement something really simple, but the actual circuit itself is complicated. So that kind of distinction is important in this sort of work. So why do we even need to do any of this? I expect most of you are aware that quantum computers are imperfect, they are noisy. So if you have some quantum circuit you want to run, if you had a perfect quantum computer, that would mean if you ran your quantum circuit on that perfect quantum computer, you'd be sampling from some distribution over bit strings. And you don't typically know what that is in advance, because otherwise, why would you be running your quantum circuit on your quantum computer? The issue is you actually have a real quantum computer that doesn't work the way it's meant to work, and you're sampling from some other distribution over bit strings, and you typically have no idea whether or not this is close to the distribution you're meant to be sampling from. And the reason it might not be close to that is that errors occur when you run circuits on real quantum computers. So each of your gates is implemented imperfectly. It might be slightly over-rotated, so it might have a coherent error, so it's systematically incorrect every time in a small way. There may be stochastic errors, such as occasionally a bit gets flipped in your circuit. There can be all sorts of different kinds of errors that can happen in your circuit that cause you to be sampling from the wrong distribution. And these two distributions are never going to be exactly equal, but you care about whether or not they're close or not. And so we can think of how well you're running this as something we might call a success probability as the distance between these distributions. And I'm putting these in scare quotes because we don't always mean precisely the distance between these distributions. There's lots of different ways we can quantify how well you've run a circuit. So I said that we were trying to measure and learn capability. So what do I mean by that? We need to kind of be a little bit precise. So I mean a quantum computer's capability is a map from the space of all possible circuits you can run on a device to the circuit's success rate on the device in question. So a quantum computer has its own capability function, and it maps quantum circuits to the success rates that you would get if you run those circuits. And success rate here might be quantified by, say, process fidelity, or some other metric for what it means to run a circuit well. So that's what I mean by this thing here. It's this capability function. And if we knew this capability function, then we would know almost everything there is to know about this quantum computer, because then you could see whether or not you could run your algorithm on this device or not, by just looking at your circuits, finding out how well they run using the capability function, and then you'd know whether your algorithm is going to run successfully. So this is really what we're trying to probe and learn as much as possible. So can we measure the capability of a quantum computer? So what if we had a circuit that we wanted to know how well you can run it? So what I mean by this is you want to basically evaluate the capability function for your quantum computer just on this one circuit. Perhaps this is like your algorithm you really want to run. So the naive benchmarking approach to this, what I'm calling it here, is you run that circuit on the quantum computer and you get samples from the distribution. And you'd also simulate it on your classical computer, and you would get samples from the exact distribution you would get if you had no errors. The problem is that this is a really inefficient thing to do. So if this is a large computationally useful circuit, you can't actually simulate it on your classical computer. That might take millions of years on the largest supercomputers. And then the experiment's also typically slow, because you might have a distribution with high entropy. You have to get a lot of samples to be able to actually see what your distribution is and see how close it is to some other distribution. So this is an extremely inefficient thing to do and is often infeasible. So the approach that we have been developing is what I call proxy programs. So the idea is that you take your computationally useful circuit or whatever circuit you're interested in, and you convert it into another kind of circuit, we're calling it a proxy program, that you can do fast experiments to sample from the distribution and a fast simulation to tell what the output distribution should be. And you can compare these. And the idea is if you design these well, that from this value, from comparing these, you can infer how well you can run this original circuit that you care about. So we're indirectly measuring how well you can run a circuit by creating some other circuits that have very similar properties. So that's the general idea of what we're doing in this work. So if any of you are familiar with this field, you may well know there's lots of really neat benchmarking techniques out there. So how does what I'm talking about fit in with all of that? There's things like randomized benchmarking, which is ubiquitous and used by pretty much every experimental group in the world. There's quantum volume, which is something IBM introduced and is now pretty famous. Cross-entropy benchmarking is what Google used in their supremacy experiments. You can also run algorithms as benchmarks to see how well your device runs that algorithm. So why do we need anything else? What's wrong with all of these? So I've already touched on some of this. So one issue is that most methods don't scale well with the number of qubits. And this can happen for a variety of different reasons. There's all sorts of reasons why they might not scale well. So randomized benchmarking doesn't scale well for a really subtle reason that is not at all obvious unless you've thought about randomized benchmarking a bit. So the way randomized benchmarking works is you run sequences of random Clifford gates from the n-qubit Clifford group. And this is efficient to simulate. So you can actually tell what you should get out from these circuits. And in fact, you design them so you should always get the input back because you end with an inversion Clifford. And so the classical computation that you need to do here is efficient, it's very straightforward. The issue is that this requires gate compilation. So an n-qubit Clifford has to be turned into 1 and 2 qubit gates. And these circuits become absolutely ginormous very quickly as you increase the number of qubits. So if you were a proponent of Clifford RB, the standard randomized benchmarking method, someone came to you and said they wanted to test 100 qubits with it, you're going to be giving them absolutely ginormous circuits to run that are just totally infeasible on any device in the near term. So this is just not going to work for that reason. We need techniques that don't require running absolutely giant circuits. Other techniques are not scalable for more straightforward reasons. So quantum volume.
Timothy, just a very quick question I'm curious about. So you mentioned that you use Clifford circuits because you can simulate them, which is of course true. But I'm curious because you also said that you run the inverse of the circuit. So you're supposed to get back to the identity. So simulating them isn't actually that important.
No, in the case of Clifford RB, simulating them is not particularly important. You sort of do have to do simulation in so much as you have to work out what this inverse is. And so that requires like doing the group operations, which is kind of a form of simulation. So it depends on exactly what you mean by simulation. But yes, like simulation is not super critical to Clifford RB.
I mean, in order to get the inverse of a circuit, you just go one by one through its components and take the adjoints.
So that is a way you can invert a circuit, and that's actually the method we use in this talk that what I'm going to be telling you about. That's not how Clifford RB works. So Clifford RB involves random, you run a sequence that's at length m, and each of those is a random element from the Clifford group. And then you have to combine all of those together and work out what the inverse of that is, and then put it at the end. So it's a little different.
Thank you.
Any other questions right now? Okay. So quantum volume and cross-entropy benchmarking, they're not scalable for a much simpler reason, which is that it requires exponentially expensive classical computations. You have to actually simulate how those circuits would run on a perfect quantum computer, and that's exponentially expensive. So in this case, you just can't go beyond about 54 qubits. It will take you thousands of years to simulate these circuits on your classical computer. So that's utterly useless for benchmarking. A more subtle point is that most of the methods that exist use random disordered circuits. So that's obviously going to be the case in something called randomized benchmarking. It's also the case in quantum volume and cross-entropy benchmarking. And the issue here is that random disordered circuits are not actually representative of how well more structured circuits will perform, which I'm going to actually show you a bit later in the talk with experiments. So if you run experiments using random circuits, you can't really predict how well you're going to run an algorithm, for example. So now I'm going to get on to telling you some of our results. So we developed this technique called circuit mirroring, which is a tool for creating proxy programs. You take a circuit and it turns it into what we call a proxy program. And the basic idea behind it is incredibly simple. You take your circuit and then you append to it the inverse of that circuit. So you run all of the layers in reverse. You run the circuit in reverse with each layer replaced with its inverse. This is a really simple way to turn a circuit that might be something very complicated into a circuit where we know exactly what its overall operation is. So the state you might create halfway through the circuit could be incredibly complicated, but because we undo that evolution, we just get back whatever we put in. This is an incredibly simple and obvious idea. We're certainly not the first people to think of this. For example, this is basically what a Losch-Schmidt echo is, which comes from the 1870s. One issue with this, and why it's never actually been used before in benchmarking, is that this is flawed due to error cancellation and addition. So what I mean by that is if you run this forward circuit imperfectly, the errors in that circuit can actually cancel out of the errors in the inverse circuit. And you can see why this is with a really simple example. Imagine if you had a completely broken quantum computer, and every time you told it to do a layer of gates, it did nothing at all. It did an identity, and it did so perfectly. Well, this circuit would work perfectly because you'd never be doing anything. You would get an identity out, you'd get all your qubits back in the zero state, but you would have actually completely and utterly failed to run this circuit. You'd have just been running identity operations the whole time. So just doing this kind of motion reversal is flawed for telling you how well you can run your original circuit. What it's telling you is how well can you undo whatever evolution you did. It's more or less a test of of coherence. Somewhat. So we don't just do this, we fix the flaws in this method. What we do is we insert a randomized central circuit that basically prevents this error cancellation effect. And then we do minor tweaks to these inversion layers, which we call a quasi-inverse, that then basically means this entire circuit still collapses down to something really simple. And it collapses down to a Pauli operator, which we can efficiently compute. Is kind of trivial computation to do classically. And so then that means you should get out some particular bit string every time you run this. We know what that bit string is. We can look to see how often you get it, and that's telling us how successful that circuit is. And we also add another element to these circuits. We add a randomized state preparation and measurement circuit for slightly more subtle reasons. That's related to guaranteeing that we're measuring the process fidelity of this circuit here. And that's because we want to interrogate how well the circuit runs with general input states, not just a fixed input state. And so these circuits have, or this ensemble of circuits has a couple of properties. So every one of these circuits is a sufficiently verifiable output. We know what it should return. And when you run these circuits and you look at the average performance of these circuits, this is actually representative of how well you can run this original circuit that you cared about. And in fact, these circuits' success probability are related to the fidelity of this circuit C. And I'm being slightly hazy here because the relationship is somewhat complicated, and I'm going to come back to that later in the talk. So this is a way to measure how well you can run any circuit that you're interested in. And so one thing you can do with this kind of technique is create scalable and flexible benchmarks to basically probe the performance of a quantum computer. So we don't just want to, we don't have a particular circuit we care about. We just want to design benchmarks that give you some overall idea of how well this device is performing. Circuit mirroring is this technique that takes a circuit and turns it into mirror circuits. So to create an actual benchmark that you can run, you need to pick some circuits to put into this. It's a procedure that turns circuits into efficiently verifiable circuits. We need to pick what circuits we're going to use for benchmarks. So there are all sorts of different things you could do. We haven't explored all the different options. I'm sure there's lots of very interesting ideas that we haven't thought of. A couple of straightforward ideas are randomized unstructured circuits and also repetitive error amplifying circuits. We basically repeat the same pattern of layers again and again. And that means that you have coherent addition of errors that are occurring in your device. You could also design application-specific benchmarks, which is something that's currently being done in our group. I'm not going to talk about that. I'm going to focus on these generic benchmarks, which we did in the Nature Physics paper. So I'm going to tell you about some experimental results for the next little while. So what we did is we benchmarked 12 publicly accessible processors using randomized mirror circuits. That's what's shown here in B. We basically pick a random circuit and then we put it into our procedure to create what we call a randomized mirror circuit. And so what we did is we benchmarked these 12 different devices. So there are 9 devices from IBM and there's 3 devices from Regretti, so each plot is for a different device. And what we're doing here is we are running varied width and depth randomized mirror circuits, and they're approximately exponentially spaced widths and depths. You can see what these are on these axes here. And what this is called is volumetric benchmarking. So this is a general idea of mapping out performance as you vary depth. And it's kind of a generalization of the quantum volume idea from IBM. And so what are we showing here? So each width and depth, so that's a single point on these grids. We sampled 40 randomized mirror circuits, and then you run each one 1,000 times to work out what its success probability is. And then what we're plotting is a thing called polarization, which is just a rescaling of this success probability P. That's the probability you get the correct bit string, and then W is its width. It's not hugely important that we're plotting polarization rather than success probability. Basically, what this means is we're removing the contribution of uniformly random outputs. If you just think of these as success probabilities, it doesn't really matter a whole lot.
Sorry, I might have missed something when you had that random circuit in the middle. Are these benchmarks designed so that they come out as pure states in the computational basis?
Yes, yeah. If you run this circuit perfectly, you should get out a bit string every time. It should be a pure state in the computational basis. Yeah. And so yes, this quantity that we're plotting here is this P is the probability that you get that correct bit string.
Thank you.
And what we plot in these plots, there are all sorts of different things you could do. What we're plotting here is the performance of the best circuit out of the 40 that we ran, the average over all 40, the average polarization, and then the worst. And so this is telling us something about the distribution over performance of similar size of the same shape circuits on the device, where shape means width and depth. And so by looking through all the details here, like exploring what you see in this figure, you can learn all sorts of things about what's going on in these devices. I'm not going to go into lots of different details here. I'll just focus on one point, which is actually really obvious, but is often overlooked implicitly in lots of things people do. So what we're showing here is that the mean performance on random circuits is not always a good predictor of performance on a randomly sampled circuit. So basically all I'm saying is that there's a significant variance in the performance of circuits of the same shape. This is really not shocking. There's no reason that there shouldn't be a variance in performance of circuits of the same shape. But this is often ignored because if you just quantify performance by an average over random circuits, then you're essentially ignoring the fact that there is variance. And that's what's done if you just run, say, randomized benchmarking and get out an average error rate for your gates. That's implicitly ignoring the fact that you have variation over performance of different circuits. And that's actually really important. And so this is visualized really clearly in these plots, I think, because what we show here is this black line here is the threshold at which, or the frontier at which the average polarization drops below 1 over E. It's a somewhat arbitrary threshold. 1 over E is nice for some reasons. The green line is the threshold at which, or the frontier at which the maximum drops below 1 over E, and the red is the frontier at which the minimum drops below 1 over E. So what you can see is that circuits start failing on this device here really early on. So you find that there are circuits on 2 qubits at depth 4 that start failing, for example. Yet you're also finding that there are circuits that succeed on 2 qubits out to depth, that's like 40. So there's a massive variance in the performance of different circuits. This isn't hugely surprising that this happens. There are very simple reasons why this would occur. So what's happening is that there's structure in the errors of the device, which we mean by that, I mean things like coherence in the errors.
What are the dates you have on the upper right of each one of those subfigures?
So one of the dates is the date at which the device became available, I believe, and then the other date is when we ran the experiments. So the more recent date is when we ran the experiments.
So all these experiments are 3 years ago?
Yes, yeah. Yeah.
Would you, I mean, I'm curious about how performance has changed actually more recently. Do you anticipate that they'll do better on these benchmarks now?
Yes, the latest, so we haven't done any systematic tests, but the more recent IBM devices do substantially better than this. So, any other questions at this point?
Yeah, I have a question. So you motivated this by trying to predict the fidelity of a particular quantum circuit. Do you have any results showing how well you were able to predict these fidelities?
Yes, I do. So that is coming up in a few slides. These results here, we weren't really even trying to predict fidelities at this point, because what we're doing here is we are using circuits as like generic benchmarks that give you a feel for overall performance of a device. So no one cares about how well you can run this random circuit. We just selected a random circuit. And so we're not even trying to infer how well you can run this random circuit. And in fact, the analysis we're using here doesn't tell you how well you can run this random circuit, because we're plotting the success probability of this entire circuit, which is twice as deep. It's going to roughly fail twice as often. So we're not even trying to infer that in this case. But yes, that is what you can do with these techniques. And yeah, I'm going to show you slides about that. So before I get onto that, one of the really neat things we think about this method is that you can create benchmarks from arbitrary circuits. So it's not just a single kind of circuits like random circuits. And so we also created a benchmark using periodic error amplifying circuits. And one of the main reasons we did this is because we wanted to demonstrate the fact that circuits other than random circuits often perform a lot worse than random circuits. So if you have highly structured circuits, they often perform worse than a random circuit. And so that is what this data here is showing. And so I'm just going to concentrate on column A, which is just comparing performance on periodic circuits and on random circuits. And so what this is the inner squares show the worst case over 40 random circuits, and then the outer squares shows the worst case over 40 periodic circuits that we sampled. And they were designed to have all of their properties as similar as possible, except one of them is random and the other is periodic. And what you can see is that the performance of the periodic circuits, the worst case, drops off much more quickly with depth than the performance of the random circuits. So the outer boxes are dropping off to red much more quickly than the inner boxes. And the reason that this is happening is almost certainly because they have coherent errors in their device. There's a question?
Yeah, thank you. So often circuits that, oh, my video is not working. Circuits that people are interested in are often, like, for example, if you do trotterized time evolution or if you do VQE, the circuits are often periodic, but sometimes the angles and the single qubit rotations could be different in the different layers.
Right.
I guess you picked the angles to all be the same, so it's exactly periodic.
Yes.
What about something that's close to periodic, where you have the same ansatz structure in each layer, but the angles are different or something?
That's a very interesting question. So what we chose to do here was try and pick the two extremes. So totally disordered circuits have the minimal addition of coherent errors. Maximally ordered circuits, so repeating the same thing again and again, that maximizes coherent addition. Our conjecture is that if you run the kind of circuits you're talking about, that are more like real algorithms that are quite periodic, but not exactly periodic, such as changing the angles, you get performance somewhere between these two. And one of my colleagues, Stefan Serton, he's designing benchmarks based on Hamiltonian simulation algorithms, and that's actually what he's seen so far. So he's putting them into this mirror circuit method, and he's found that their performance is somewhere between these two.
Thank you.
So Tim, I have a question.
Yep.
So by having this this benchmark using the mirror circuits, maybe I asked this question before. If I have 20 systems to choose from, I run the benchmark and I will go with the one that does the best, right? But if my 20 systems all more or less do roughly badly, right? Can I figure out what I can do to improve my systems? Would that be what one would ultimately like to know, right?
So these methods are their main purpose is to
Just to judge.
it's to judge how well things are performing. That's kind of what they're
Right.
usually designed for, but that's not all you can do with them, because by running various kinds of benchmarks, you can kind of learn what's going on.
Right.
For example, you can work out that you have large crosstalk errors when you see performance drop off as you increase the number of qubits more quickly than you'd expect. You can learn you have coherent errors by looking at these kinds of plots and seeing this kind of drop off. If you want to know exactly what's happening and how to fix it, then you want to use like a characterization technique that tells you exactly what's going on. So various kinds of tomography. But this is sort of like a complement to those, because tomography techniques are much more intensive and challenging. And so you can run, for example, tomography techniques, learn what you can. You can also run these kinds of things that are more scalable, and they're kind of cross-validation for each other. You might discover new errors from running these kinds of techniques, and then you will know how to go and explore them using like some more specialist tool.
Looks like there are questions.
Yeah, another quick question. I'm curious about this periodicity result. For these, for these intermediate circuits, there's probably more than one way to transpile them. And so I'm wondering, your results suggest that this transpilation is deterministic, that they're transpiled exactly the same way on each repetition. So the first part of the question is, have you checked that? And the second part is, given that the performance is worse for these periodic circuits because of the correlated hardware problems you mentioned, would it be preferable if you added a random element to the transpilation so that they weren't transpiled exactly the same each time they occur?
Those are both excellent questions. So the first one about the transpilation, we did everything possible to make sure that they are running exactly the same like sequence of like pulses each time we run the circuit. So for example, when you run an IBM, you can turn off all their transpilation and give them the exact open chasm they're meant to run. Now, we don't have access to the device, so I can't promise you that's what they did, but the results are consistent with that being what they did, and that's the best of our understanding what was done in these experiments. In terms of the other question about adding in randomization, so this is a thing that is, lots of people think is a good idea, adding randomization in. There are various ways you can do randomization, lots of different kinds of like randomized compilation techniques. I think it's a matter of perspective, because randomized compilation, basically you're going to get like an average performance, and you can always do better than that average by finding whichever circuit performs the best. The question is, can you work that out, or is it too hard? So because it's not that all periodic circuits perform worse, here we're plotting the worst case. Some of the periodic circuits perform better than random circuits. And so if you can find the correct compilation for your circuit, you might be able to do much, much better than if you added randomization into your compilation. But it's a very hard problem. So I'd say it's an open question.
And the optimum might be time dependent, depending on how the hardware drifts.
Exactly.
Good.
Another question, Elliot?
Yeah, thank you. So regarding the pulse sequence, many of these devices do have open pulse access, at least the newer ones often do. So you could actually like control the sequence of pulses that's sent to the device. Yeah, also, I would think that it might be more useful than just like understanding how well the device is performing to be able to estimate these fidelities. For example, if you do tricks like randomized compiling, for example, polytwirling, and you can like convert your noise channel into a global depolarizing channel, then if you know the fidelity, then you can do error mitigation and you can like recover the mitigated expectation value if you're observable. So like knowing that fidelity could be very useful.
Yeah, agreed. There are definitely other uses for knowing these fidelities. And for example, like you can test how well like your some kind of like improved pulse scheme works by comparing the fidelity of your circuit with and without that pulse scheme. There's all sorts of things you can do. So yeah, I agree. There are lots of uses to knowing this fidelity. And in terms of the open pulse question, I think that was only available on 1 qubit devices when we did this at the time. But yeah, that's a good point that you can do this kind of pulse level control on some of these devices now, which is great.
Thank you.
So the last bit on this part of the talk is something that we call capability regions. So these benchmarks that we run, we think that they're good for both learning details, like some level of detail about what's going on, but also one of their main purposes is to have like easy to understand high level summaries of how well a device works. So we implemented these things called capability regions for that. And so what these are showing is the regions in which all the circuits of a particular shape ran successfully. So those are the green regions. Orange is where some of them did and some of them didn't. And the white region is where none of the circuits ran successfully that were that shape. And so you can actually think of this as a simple projection of the capability function. So we've learned the capability function at certain values in the circuit space by doing experiments to see exactly what that value of the capability function is. And then this is a high dimensional object. And what we've done is we've projected it onto this 2D grid so that you can kind of visualize how well these devices work. And this is obviously hiding lots of details about what's going on, but we think it's quite a nice high-level summary of what you can and can't do with these devices. Because if you're interested in running some algorithm that has 14 qubits and requires a depth of 128, I mean, no useful algorithm can be done there, but just imagine if you're interested, you can see that you can't do that on Melbourne. You're just going to get absolute junk out if you do that. And whereas if you're down here, you'll perhaps get useful data out. So I think this is kind of a good way to summarize how well devices are working. That's kind of more informative than something like quantum volume, but it's still kind of very straightforward to understand. So I'm now going to move on to telling you about using mirror circuits to estimate algorithm execution fidelity, which we've already had some questions on. The first part, I'm going to tell you about estimating the infidelity of random layers, and then I'm going to talk about how you can estimate the fidelity of complete circuits. So I think I'm going to skim over this little bit fairly quickly, the infidelity of layers. So the idea is that you can use randomized mirror circuits as a randomized benchmarking protocol, which kind of has a special meaning in the community. So the idea meaning that you run random circuits of varied lengths, and then you compute the average success probability over circuits of the same depth, and then you plot this versus depth, and then you fit an exponential decay to it. And so there's a whole community working on different kinds of randomized benchmarking protocol, and we think randomized mirror circuits make a really good method for doing this. So this is showing data on up to 16 qubits on an IBM device, and we compute this thing called effective polarization, which is a slightly more complicated version of what I was talking about before, where we take into account the Hamming distance of the output bit stream from the target bit stream. And we've shown that by doing this, you can actually estimate the average infidelity of a random layer. So I think this is a pretty huge improvement on traditional RB methods. That's because traditional RB only scales to about 4 or 5 qubits, which is being shown here in this experimental data we took for this paper. So this bottom plot here is showing decay curves for standard RB, and it's on a log plot, which is why the exponentials look unusual. You can see that what happens is the shortest circuit you can run, which we call benchmark depth 1, benchmark depth 0, and then we have 1 done on a log scale, which is a random n-qubit Clifford, and then its inverse. That's the minimum you can do in standard RB. You see that this thing drops off precipitously, this initial polarization. So once you get to 5 qubits, you basically can't like, get anything useful out. This is just a flat line at 0. You can't learn about the performance with data like that. With our technique, you get this much more gentle drop off of the number of qubits in this initial polarization, and you can get these nice clean exponentials and get up the error rate per layer. And this scales to like hundreds or thousands of qubits. Basically, it scales as like the 1 over the error rate. So here's just a quick demo to show that this does actually scale. So we did simulations on 225 qubits. These simulations involve use only Clifford gates, and the error model is polystochastic errors, because otherwise we wouldn't be able to simulate this many qubits. And what we're demonstrating here, that each point is a different realization of our protocol with a new random error model, a new set of random circuits. We go through that whole exponential decay fitting. We get out our error rate from fitting the exponential decay. It's just the decay rate. And so what we're showing is the error rate that we get out from our method versus the exact average error rate of the n-qubit circuit layers. And what we see is we do a pretty good job of getting the right answer. We systematically slightly underestimate it for some subtle reasons that we think we actually do know how to fix in an updated version of the method. But randomized benchmarking is really kind of like a blunt tool for getting an overall idea of how well your device performs. So a small underestimate of your error rate kind of doesn't matter. These are like, they're not being used for like, I don't know, bounding whether or not you have qubits that will work in a quantum error correction code. Really, it's just like, how good is this device, more or less? That's kind of what RB is used for experimentally. So we think this is basically good enough. So I think this is a useful tool for quantifying gate performance, but a quantum circuit's failure rate is not generally the sum of the error rates of its gates. That was implicitly part of the earlier part of this talk. And so we can't just do this and then add up error rates for the layers to predict how well an overall circuit will perform. So I'm now going to tell you how we can actually do that, how we can measure the overall execution fidelity. So the idea here is we have some circuit we're interested in, there's some device we want to run it on, and we want to know, are we going to get a low error output from that? So there's lots of techniques actually for answering this question, or there's at least a few of them, some really nice ideas. There's things like cryptographic prover verifier protocols, which are really cool. There's the trap circuits from Sandia, and there's some very special purpose techniques out there that work for special kinds of circuits. But existing techniques have a variety of limitations. So for example, these cryptographic prover verifier techniques, they're really neat, and they may be very useful in the distant future of fault tolerant quantum computers, but they have some overhead associated with them. So from my perspective, they're not particularly practical right now. So our technique for estimating fidelity is a little complicated, because you can't just run this one of these mirror circuits and infer the fidelity. You have to do a few different things to be able to back that up. And so what we do is we take our target circuit that we're interested in, and then we construct a few different ingredient circuits that we're going to put together in a few different kinds of mirror circuit. So the first of these is a randomly compiled version of our circuit. So that means inserting random Pauli gates in the circuit. We also create a randomly compiled version of the inverse of the circuit. And then we also have these two random state preparation and measurement circuits that allow us to probe with locally randomized states. And so then we put these together in 3 different circuit ensembles. So the first of them consists of all of them have the randomized state preparation and measurement. The first of them consists of our target circuit, whose fidelity we want to know. And we do not randomly compile that. We want to know what its fidelity is, run however you want to run that circuit. That is not specified by our method. You run that circuit how you want. Then we follow that with this randomly compiled inverse. And the reason we do randomized compilation here is that prevents systematic addition and cancellation of errors between these 2 parts of the circuit. But then we also need this approximately, the success rate of these circuits approximately just equals the fidelity of the different parts because of the way we've designed it. So you get a fidelity of these like state preparation and measurement parts, fidelity of the circuit we care about, and the fidelity of this randomly compiled inverse by the way we've implemented these. But we want to know this thing here, the fidelity of this, since we need to get rid of these other 2 parts. And so we run a couple of other circuit ensembles to allow us to estimate those. So one of them involves randomly compiling the forward circuit and backward circuit. And these fidelities also basically decompose like this. And the fidelities of the randomly compiled forward and backward circuit are basically equal because of the fact that they're just the same circuit in a different order. And critically, we have randomized compilation, which prevents coherent addition of errors, which can happen differently in a forwards and backwards version of the same circuit. But these are stochastic errors now, and so they don't coherently combine. And then finally, we just run this state preparation and measurement circuit to estimate this fidelity. And then these three approximate formulas, you just put them together in the right way like this, you get the fidelity of this target circuit. And so you just have to sample circuits from these three ensembles, run them, use this formula to estimate the fidelity. So how does this actually work? Because our formula is not exact, except under strong assumptions, we can prove that it is approximately true under a variety of circumstances, but it's only exactly true under some strong assumptions. And so we've tested it in simulations. So what I'm showing here is three different examples of QAOA circuits with three different error models. So each point here is a random QAOA circuit that we generated and a random simulated under a random error model. And we can compute its true process fidelity because it's an error model. And then we can also predict the fidelity by running our procedure. There's a question from Elliot.
Did you also test it on actual quantum computers?
We have not done that yet. The reason for not doing that is that it is somewhat complicated to reliably estimate the process fidelity in an independent way. So, for example, quantum process tomography has like issues with it. We could do gate set tomography, which will probably, which is something we're interested in doing. So we'd run gate set tomography alongside our technique and confirm that you get the same results. That's kind of limited to 3, maybe 4 qubits. One thing that we are interested in doing is comparing this to direct fidelity estimation, which is efficient when you consider only Clifford circuits. So that's another technique that is like independent of ours, and that works for Clifford circuits. That also has an issue that it is not robust to state preparation and measurement error, so we might expect some discrepancy. So designing a good experiment to confirm this is a little bit complicated, but that is kind of the next step. We want to see how.
I guess you'll need to combine it with like standard readout error mitigation.
Right, that's one way to remove, say, readout error from a direct fidelity estimate of the fidelity. So yes, that's something I'm very interested in seeing how well it works in practice, because obviously real world devices have more complicated errors, such as like they have non-Markovian errors, which we haven't simulated any non-Markovian errors. So how well does it work when you have these kinds of subtle errors going on?
Okay, yeah, because I mean, that's really the thing we want to know, is whether this actually works on the devices.
Yeah, I agree. I mean, a prerequisite for knowing whether it works on a real device is whether it actually works in theory within a controlled circumstance as well. So understanding whether or not we should even expect this to work on a real device is a useful starting point.
Another quick question. How well does this method scale with the number of qubits?
So the scaling is constant in the number of qubits in terms of the sample complexity. So what it is not constant in is the true fidelity. So this method works well in as long as the true process fidelity is bounded. So I can't remember the exact result, it's in the paper, but the complexity scales, like it gets worse as your fidelity gets lower. Basically, you can think of that as the fact that because we're running circuits that are twice as long, the fidelity that we're measuring is basically a square of this fidelity. And so you start needing like a square root of as much data, a square of much data, whichever way around that works.
Okay.
But yeah, and if you're in this sort of like regime of, I don't know, above like 10% fidelity for your circuit, then this is like totally efficient for sampling. We actually have simulations with 100 qubits. They're not in this talk because they only got finished a couple of days ago, and we have to put things through review and approval. So they're not on this slide deck, but we have simulations of 100 qubits that is for a stochastic power error model because that's necessary so that we can simulate them. And we get something that looks exactly like this as well, just data on the diagonal. So we get really good performance with stochastic power errors, like as far as I'm concerned, for all practical purposes, this is good enough. It's bang on the diagonal, it's not exact, but no, I mean, it depends on, like, what is good enough depends on your purposes, but as far as I'm concerned, this is good enough. We get pretty good performance with Hamiltonian and stochastic errors, which is the most relevant in like physical devices, and then performance drops off significantly with Hamiltonian errors, but the relative error is still pretty small. So I think in all cases, the relative error is like below 50%. So this, whether or not that's a problem, depends on perspective, how well you need to know your fidelity. For example, you can bound your fidelity by taking a more pessimistic view on your predicted fidelity, say square rooting it. And this is the actual formula we are using, which is somewhat more complicated than I showed in the previous slides, but the ways in which it's more complicated are actually not of that much importance, the kind of technical details. So I think we're nearly at time, so I don't know if I should continue through these few slides that will take about 5 to 10 minutes, or if you'd like me to just stop.
I think 5 to 10 minutes will be okay.
Okay, right, I'll just zoom through them then. So finally, I'm going to tell you about some work that's ongoing, that's about learning a quantum computer's capability using neural networks. So this work's going to be posted on arXiv sometime this summer, we hope. So the idea here is that we're training neural networks on labeled data that has like a circuit along with its fidelity. So that's the kind of data we can extract using the methods I've just been telling you about. And the idea is we want to train on this labeled data to then predict the fidelity of circuits that we haven't yet tested. So the general idea is that we're going to input a quantum circuit into a neural network, and then that neural network is going to output the success rate, or more precisely, the fidelity of the quantum circuit. And there are many, many different ways you can do this. There are lots of kinds of neural networks. There are lots of kinds of ways you can encode a circuit, and so on. What we have been looking at mostly is convolutional neural networks, where we encode the quantum circuit as an image. And so the idea is that each row corresponds to a single qubit, and then each color corresponds to a single type of gate, and then the image is divided into one channel for each color. So here I think there's 26 channels because there's 26 different gates. And then this image is then fed into layers of convolutional filters, which are interspersed with like max pooling and averaging layers and things like that. And then the output of this is then input into a standard dense neural network. And then at the bottom of the dense neural network, we get this single number between 0 and 1, which is the fidelity or success rate. And so we can train these neural networks because we can create labeled data using our circuit mirroring method. We can take a circuit and we can run experiments to work out what its fidelity is and label that circuit. So we can create a labeled data set and use that to train the network. And so I'm just going to very briefly show you some results of doing this. So we have done this with 100 qubit simulated data using stochastic errors. And so what's being shown on the left here is the predictions from the convolutional neural network. And what's being shown on the right is a standard technique. This is called an error rates model, which basically means each gate is modeled by an error rate, and then you sum up the error rates of all the gates more or less to predict the overall circuit performance, and you find the best fit error rates. You fit that model to the data, so you learn those error rates. And so this is plotting the training, validation, and test data, which is maybe somewhat unhelpful, but the green data is the test data. So that's the data you kind of care about the performance on. And so the top one is simulations with stochastic errors. The bottom plot is 5 qubit experimental data. And what we are seeing here is we are not doing as well as with the stochastic errors. We get substantially more scatter, but we are still doing substantially better than a standard technique that scales. And in fact, what we're doing in these experiments, this data set is somewhat more challenging to model than true fidelities, because we're actually trying to model success probabilities in mirror circuits rather than after doing this various averaging and analysis of fidelities. So we think we might actually do significantly better if we had proper fidelity data. The reason we've been working with these success probabilities, these are it's just for simplicity. We already have this data. This is exactly one. This is one of those data sets I showed you at the very start of the talk on those volumetric benchmarking plots. So we have all that data, so we're using it.
So Tim, I want to understand this better.
Yep.
So the vertical axis on the right, with what you call standard technique, is simple sort of arithmetic that you do with error rates. That's how you are predicting on the right column.
Yep.
And the horizontal axis is based on your mirror circuit, what is it? Characterization.
Right. So this is the measured predictive success probability by running that circuit. And so these are the data. In this case, all of the data is actually just like raw data from mirror circuits. So we have a true success probability that's this axis. Sorry, I think I said it the wrong way around. So that is the, you've run that particular mirror circuit 1,000 times. You look at the number of times it's successful. So that's the true success probability. And then this is the prediction of the model for how the circuit will succeed.
So both of these are ideas to try to have guess the success probability without doing the experiment, because experiment is expensive.
Right. Exactly.
And then there is a comparison of how well the two ways of predicting compare CNN versus error rate standard technique. But there will be also a comparison of which one is easier to use. And I imagine the standard error rate technique is cheaper or simpler, I don't know, more straightforward, dumber, something.
So I guess this all depends on how much effort you put into the CNN. So so the error rates model involves maximum likelihood estimation of a model.
Oh, I see. Okay.
So if you just take the error rates that you were given by a manufacturer, this is an absolute catastrophe, these predictions. They're much, much worse. So what we're doing here is we train the error rates model on the training data. And to do that training, you do maximum likelihood estimation of the parameters. Like there's a likelihood function, we can maximize it. It's not super expensive, but like it takes a while, like a few minutes.
It's expensive.
Right.
Okay. I see.
And the CNNs, it just depends on how much effort you put into finding the best CNN. So like in this case, it was like a hard-coded CNN structure, and this training took like a minute on my laptop or something. I think with this experimental data I'm showing you here, I think there's a lot of hyperparameter tuning, and this might have taken like a couple of hours to do. So we certainly have not in any way perfected these like CNN methods yet. So I really don't know how expensive they will ultimately be as when we make them as good as we know how to make them. But like they may or may not be quite expensive.
Do you have any idea why CNN does not perform as well with experimental data? Maybe just because the errors are more correlated and more, I don't know, complicated?
Yes, that is almost certainly the answer. So we know that these devices have very large, like a large proportion of their error is coherent error. And coherent error, it matters how it adds up across the entire circuit. So this is like a very like non-local aspect of the circuit. The coherent error that happens at the start of the circuit can in principle cancel with something that happens like at the very end of the circuit. And so this is a complicated thing to learn. Whereas stochastic errors, basically stochastic errors more or less. Right. So we're doing so well on stochastic errors because they're pretty simple to model. So you can it's kind of, when you think about the structure of a CNN, you can kind of realize that stochastic Pauli error models are something that can be sort of learned from the image with a convolution to a good approximation. Whereas there's no reason really to believe that it can learn a coherent error model correctly. So I think if we wanted to see good performance on with coherent errors, we're probably going to do something other than a CNN. And in fact, we don't think that these CNNs are like the answer, and like
But
the
it's your first step, right? Because it was.
first step.
Yeah.
Got to do something first.
Yeah, absolutely.
See how well it works. So.
Yeah, no, it's awesome. Yeah. Right. Okay, continue. Just wanted to understand what's going on.
And something we're actually looking into doing now is doing creating a data set that uses randomized compilation, an experimental data set, because that should enforce the errors to be polystochastic. That's kind of the point in randomized compilation. And so we're hoping when we generate that experimental data set, that we're going to see performance much closer to this than this. We'll see, because we haven't done it yet. And it's going to depend on the amount of data. Like there's more data here than there is here. And we're still trying to understand how much data do we need to train these neural networks well. Like these are all questions that are still somewhat up in the air. So that was everything I had to talk about. So I'll just very quickly summarize. So hopefully I persuaded you that a quantum computer's capability is difficult to predict and it's difficult to measure just the capability for a quantum computer to run a particular circuit. So simple models of performance, such as summing of error rates, just aren't accurate. And just checking how well a quantum computer ran a particular circuit is really hard to do. So we've developed this technique called circuit mirroring. It converts arbitrary circuits into an efficiently verifiable circuit. And it enables lots of different things. So we can build scalable benchmarks from an algorithm. We can develop scalable randomized benchmarks. We can also do this scalable algorithm verification where we measure the process fidelity for which you can run an algorithm. One of the core results from our experiments is that performance on random circuits is not predictive of performance on non-random circuits. And again, this is not very surprising, but some people are surprised by it. So we're trying to hammer home this message. And finally, I told you briefly about how we can use mirror circuit data to train neural networks to predict how well untested circuits will perform. And that's still early stage research, but we're kind of excited about how it's working so far. These are the references for anyone who's interested in looking at the published works. And then finally, the team involved with this, there's lots of people at the Quantum Performance Lab. Also thanks to IBM and Rigetti for access to their devices. It's super helpful being able to try all these things out, even on small devices. It's really helpful. If anyone's interested in actually like trying out any of these methods, most of them are in Pigsty, which is this software that Sandia creates. And then finally, we're currently hiring postdocs. So if you are interested or know anyone who's interested in doing work in this area, then please let them know. Thanks, and I'm happy to take questions, but obviously we're a little over time, so.
Thank you. Paul has a question.
Yeah, just very quickly, you talked a lot about the depth and the width of the quantum circuits. I'm just curious, what was the depth and width of your CNN?
In this case, we were doing hyperparameter tuning, so I don't know what the final case, what they look like, the final versions, but we were using between 1 and about 5 convolutional layers. And then I think about between like 3 and 6 dense layers, and they were having between like 5,000 and like 100,000 weights or so to tune.
So was the width the same as the number of qubits? That was actually my question.
The input to the top is an image that is the width is the number of qubits, and then the depth is the depth of the circuit, or actually it's the depth of the largest circuit in the data set. And then the convolutional filter just has to be smaller than that size, because the convolution like moves over the image and convolves with the image. So you just need a filter that is smaller than the size of the image. So you don't have to scale up the size of the filter with the number of circuits.
So the image, I didn't realize the image would contain basically, what we would call the entire time evolution of the circuit.
Yes, it contains all that information.
Great.
Leo, you can ask a question.
So would the image size be different for every single circuit that you input?
So no, it isn't, because at least the standard way of doing these CNNs doesn't allow you to vary the image size. So what we do is if the circuit is smaller than the maximum circuit, it just gets embedded inside a larger image where like all the values are 0 outside of that circuit.
Oh, I see. So you set a really big image and have all zeros. I see. Have you ever tried to use like a saliency method to figure out what kind of like parts in the image that the neural network focuses on to show like that is indicative of the success rate? Like what does it focus on and stuff like that?
So some analysis like this was done quite a while back. I mean, it was like last summer. But we then realized that our CNN just weren't working properly. In fact, we were training them incorrectly. I wasn't using neural networks and was training them in the wrong way. And so all of that analysis was basically useless. And we've only really got neural networks that are working reasonably well over the last couple of months. So we haven't done that analysis yet. So that's very interesting to know why, like, what are these neural networks learning? And I don't know yet.
Okay, thank you.
So Tim, I imagine postdoc at Sandia could be working anywhere because you guys are all delocalized, correct?
Yeah, we are all over the country in every time zone.
So they don't have to be in New Mexico.
They don't, no.
Yeah, Robin told me 2 years ago he lives on the East Coast.
Right, he moved, quite a while ago. I moved to Chicago like a few months before the pandemic. And yeah, now since then, I think every staff member in our like QPL group has moved, and none of us now live in, I guess Kevin Young lives near the Livermore site, but everybody else has like moved. So we're completely dispersed and entirely used to like Zoom meetings and that sort of thing.
Do you get together in person like on once in a while, like on a monthly basis or so?
Yeah, so actually we are having a retreat in Utah next week. This is the first time we've met up, except for March meeting. The first time we've all met up since before the pandemic. So we're sort of, and it's the first time we've met up since we had like postdocs and grad students working with us. It was working out how this is going to work, but it's starting from next week. We're going to be having retreats.
I see. Very cool. Well, thank you so much.
Very welcome.
For coming and giving us this talk, and look forward to hearing more about the new results once you have the preprint.
Yeah, and if anyone has any questions, definitely feel free to email me. You were a delightful audience with really insightful questions.
Thank you. Bye, Tim. Until later.
Thanks very much.